Hey guys, Mr. B here, and in this video we're going to be going through the final section of chapter 12 on limiting reactants and percent yield. Now this video is going to be again a bit longer just because this chapter in general has a lot of math to it. There's a lot of problems where we have used a lot of concepts from previous chapters that we have learned in this course, and I just wanted to make sure that I take my time, go through each problem, and explain it well so that you understand it and you're not confused. All right, so please, I encourage you to watch this whole entire video. Really take the time to understand and watch through the problems so that you can see how they're solved. That way when you go do your practice, you're not confused. Okay, so this final section on a limiting reagent or reactant, okay, that word is, you'll see it both ways, and percent yield is going to be talking about in chemical reactions, sometimes, or I guess every time, when you have a chemical reaction happen, the two materials that you're starting with are not going to both run out equally. Okay, so like this picture here that they're showing at the beginning says if a carpenter had 2 tabletops and 7 table legs, he could only build 1 4-legged table. The number of table legs is the limiting factor in the construction of 4-legged tables. Similarly, in chemistry, the amount of product that you make in a reaction will be limited by the amount of one or more of the reactants. So basically this image of the guy with the table and what they're trying to relate to chemistry is saying when you have a chemical reaction happen, you have a certain amount of materials that you're beginning with, but the reaction, the chemical reaction, is eventually going to stop when one of those two things runs out first. Okay, both of them will not run out at the same time, unless of course you calculated it and planned it out to be that way, which most likely you didn't. One of those things will be gone first. And when one of those materials runs out, the chemical reaction is going to stop. And so we call that material the limiting reactant. Okay, and we're going to learn how do we calculate and how do we figure out which one that one will be, and then ultimately how do we calculate how much product then we can make based on the amount of stuff that we're starting with. So limiting and excess reagents or reactants. Okay, again, you're going to hear that both ways. So in a chemical reaction, an insufficient quantity of any of the reactants will limit the amount of product that you can form. The limiting reagent or limiting reactant is the reagent or reactant that determines the amount of product that can be formed by a reaction. Okay, so again, the limiting reactant is the material that is going to run out first. And when that material runs out, the reaction will stop. And the amount of product that you've made up to that point, that is the maximum amount that you can make, because no more product will be made anymore because your chemical reaction is no longer going to take place. So in the reaction of nitrogen and hydrogen, they mentioned hydrogen is a limiting reagent. Okay, so first off, let's type this reaction out so we actually know what the heck they're talking about. Okay, so we have H2 plus N2 makes NH3. And balancing wise, we need a 2 there and a 3 there. Okay, all right, so in this reaction, they're basically saying hydrogen is the material that's going to run out first, and nitrogen is the one that will not be completely used up. So you're going to have some left over. Okay, this is what we call the excess reagent or the excess reactant. It's the material that doesn't run out first, that there's going to be some left over, and that's what you have in excess. Okay, now we're going to go through how do we know that hydrogen is the limiting reactant, and we'll go through some practice problems again so we understand how we know this. So here's the reaction shown between nitrogen, hydrogen, making ammonia. Okay, so N2 plus 3H2 makes 2NH3. So again, this is basically saying 1 mole of N2, or 1 molecule of N2, if you want to think about it in molecules, you'll need 1 molecule of N2, 3 molecules of H2, and you'll make 2 molecules of ammonia, okay, NH3. So imagine that before the reaction starts, we have 2 molecules of N2 and 3 molecules of H2. Okay, so this is like these two things are sitting there and they have not reacted yet. If we know that the ratio between nitrogen and hydrogen in this reaction is 1 to 3, for every 1 molecule of N2 that we start with, we're going to need 3 molecules of H2 to react, right? So if that's the case, given the amount we're starting with here, 2 molecules of N2 and 3 molecules of H2, the molecules of H2 will be our limiting reactant because one of these molecules of N2 will react with all 3 of these molecules of H2 to make our 2 molecules of ammonia, and we're still going to have one molecule of N2 left over. And this reaction could keep on going if we had more hydrogen. But unfortunately, we only had 3 molecules to begin with, and those 3 were used up when we reacted it with the first molecule of N2. Therefore, H2 is now gone, and our reaction cannot continue anymore. Therefore, our H2 is our limiting reactant. Okay? Our hydrogen is limiting. If we had another 3 molecules of H2 on hand, we could react that then with the other molecule of N2 and make 2 more molecules of NH3, in which case both of these things then would be gone and we'd have no limiting reactant. Okay? But again, in this example, our H2 is limiting and our N2 is in excess. Okay, so let's take a look at a classic example of a type of problem from this chapter section so we can understand what we do, okay? Now, I am going to do these on paper just because it's hard to type all this stuff out. It's easier and faster for me to do it by hand, so I am going to be switching my camera over to my desk cam where I can do this on paper. All right, so they have an image here. It says copper reacts with sulfur to form copper 1 sulfide according to the following balanced equation. They're giving that to us here. Says, what is the limiting reagent when 80 grams of copper reacts with 25 grams of sulfur? Okay, so like I said, I am going to be switching over to my desk cam here. So let's make a real quick switch. Okay, so we are starting. I'm going to write up the reaction so we have it. Okay, so we have 2 CuS plus sulfur makes Cu2S solid. Okay, so here's our reaction from the problem. And they're telling us that we are starting with 80 grams of copper. Okay, so we have 80 grams of this material. And we have 25 grams. I'll do this in another color just to make it stand out. We have 25 grams of sulfur. Okay. The question is asking which one of these two is limiting. All right, so to do this, here's what we're going to do. So this is, first off, what we are given. Okay, so our given quantities are 80 grams of copper and 25 grams of sulfur. Now the question really we need to ask ourselves is, if we start with 80 grams of copper, how many grams of sulfur do we need to react with 80 grams? Okay, now we're given 80 grams of copper and 25 grams of sulfur, but that does not mean that we need 25 grams of sulfur to react with this copper. We could need more, we could need less. So step 1 in these types of problems, okay, which is step 1 in all of these types of problems from this chapter, is always convert to moles. Okay, so step 1, we'll write this over here. Okay, so that way you have these steps. So step 1, convert to moles. Okay, that's always going to be step 1. So let's convert our grams into moles of our grams of copper into moles of copper. Looking at the periodic table, copper has a molar mass of 63.5 grams per mole. Okay. Now again, if you don't have your periodic table on hand for this, I would recommend pulling it out. We'll also convert our grams of sulfur into moles of sulfur. Okay. So sulfur has a molar mass of 32 grams per mole. Okay, so we'll write out our math work. Let's do our calculation here real quick. I'm just going to use my cell phone. So we're going to take 80 grams, divide that by 63.5. Okay, and let's just round to 3 sig figs. So let's go 1.26 moles of copper. And again, this is still what we are given. Okay, so we're given this. And as for our sulfur, 25 grams divided by 32 grams, we get 0.781 moles of sulfur. Okay, so step 1 again is still going to be convert to moles. Now, once we have moles, the next step is we need to figure out, if we have 1.26 moles of copper, how many moles of sulfur do we need to react with this? Okay, now this is basically similar to the problems that we dealt with in chapter 12, section 2. So what we're going to do is we're going to convert moles of copper to moles of sulfur. Okay, so basically what we're going to do is we're going to say if we're given this many moles of copper, how many moles of sulfur do we need? Now in this reaction, it's a 2-to-1 ratio. So for every 2 moles of copper, we need 1 mole of sulfur. Basically saying for every 2 moles of copper, we only need half the amount of sulfur. Okay, so we're going to do this. We're going to do this conversion out, and our conversion factor is 2 moles of copper to 1 mole of sulfur. Seeing as I'm starting with moles of copper, I'll put my 2 moles of copper on the bottom and my 1 mole of sulfur on the top. Okay, like this. So if I do this math out, my moles of copper will cancel, and I'm going to take 1.26. Okay, so we're going to take 1.26, divide by 2, and we get 0.63 moles of sulfur. Now this number that we just calculated, this is how much we need. Okay, this is how many moles of sulfur we need to react with this many moles of copper to begin with. So now let's take a look at what we are given here. Okay, so remember, this many moles of sulfur, that was how much we're starting with. Okay, we're starting with 25 grams. We just converted it to moles. After this first calculation, it says right here that we need 0.63 moles of sulfur if we want to react it with this many grams of copper. We are being given 0.781 moles of sulfur. So now we just look at these two and we just compare. Okay, we just compare. Do we have enough sulfur? Yes. We only need 0.63 moles, and we have 0.781 moles, which means of these two, this is going to be in excess because we have enough, and the copper is going to be limiting. Okay, so copper is going to be our limiting reactant. Now, we'll also, however, do this math out just to see if we have this many grams of sulfur, or this many moles, how many moles of copper would we need? Okay, so let's do the other way around too, just to make sure that we are going to be correct here. So I'm just going to write this down here just because I have some stuff written here now. So 0.781 moles of sulfur. Okay, that's what we're given. If we convert moles of sulfur into moles of copper, okay, so it's like this, converting moles of sulfur now to moles of copper. Okay, so just flip this around. Again, it's a 2-to-1 ratio. So for every 1 mole of sulfur, we need double the amount of copper. So for every 1 mole of sulfur, okay, I'm going to write that on the bottom, we need 2 moles of copper. Okay. Again, this here is coming from this ratio, 2 to 1. So if we take 0.781, okay, so 0.781, and times that by 2, we need 1.5, I'm going to round to 2 sig figs, so 1.56 moles of copper. Okay, again, this is what we need. Okay, this is what we need. So if we are starting with 25 grams of sulfur, we need 1.56 moles of copper. And looking at what we are given up here, which we calculated already, we only have 1.26 moles of copper, but we need 1.56, which means we don't have enough, which is why copper is limiting. Okay? So again, we can go, let's just make sure that this is very clear. Okay? So we were comparing these two numbers to each other to see did we have enough, and then we're also comparing these two numbers to each other to see if we have enough. Okay, compare. Okay, so this is kind of the problem, and this is how we want to work it. First step, again, is always to convert to moles. Okay, always. That's first step in like every one of these problems in this chapter. Step 2, convert moles of one material to moles of another material. And then step 3 basically is compare what we are given to what we need. Okay, so what you're given is what you're starting with. And what you need is after you do your conversion and you convert from one mixture to another, that's what you need. Okay, and then you just compare the two and you see, do you have enough or do you not have enough? Okay, so let's switch back to our slides here. Okay, we're back. All right, here we are. What is a limiting reagent when 80 grams of copper reacts with 25 grams of sulfur? We did this math work, of course, on our paper, but we are going to write in here that copper is limiting, just so we can have that there, okay? But the math work, again, was shown on our paper. So, all right. So now let's take a look at the next example problem. So now this question is saying, using your limiting reagent to find the quantity of product. So what is then the maximum number of grams of copper 1 sulfide that can be formed when 80 grams of copper reacts with 25 grams of sulfur? Okay, so this problem now is basically saying, all right, you figured out that copper is limiting. But if that is true, if copper is limiting, then how much product can you make, right? So we're basically going to do the math again on paper, but what we're going to do is we're going to take the amount of copper that we're beginning with, and we're going to just do a calculation to go from grams of copper to grams of copper 2 sulfur or copper 1 sulfide. Okay, so switch back to our paper. Again, I'm going to write the reaction out so that we can see it. So again, our reaction was 2 copper solid plus sulfur solid, and we make copper 1 sulfide solid. Okay, now basically what this question is asking us to do is saying we have 80 grams of copper and we have 25 grams of sulfur. And the question is basically saying, how many grams of copper 1 sulfide can you make? So the first thing that we would need to do is find out which one of these two is limiting. Now, fortunately for us, we found that out in the previous problem. Okay, we know that this is our limiting reactant. So from this then and going forward, we're going to start with this number, and we're basically going to go from grams of copper to grams of copper 1 sulfide. Okay, and we're basically just going to ignore this. Okay, this number is just completely irrelevant. It doesn't matter. Because it has no effect. Okay, this is the only one that matters because this is what's going to run out first. So now it's just like a problem from the earlier parts of the chapter. Okay, so step 1 is always going to be convert to moles. So convert to moles of copper. Step 2 is going to be convert moles of copper to moles of copper 1 sulfide. And then step 3 is going to be to convert those moles back into grams. Okay, so step 3 is convert moles of copper 1 sulfide to grams of copper 1 sulfide. Okay, just like in the previous section of the chapter. Okay, so converting from our 80 grams of copper to moles of copper. Now we actually already did this in the previous problem. That was the first step we did in the previous problem, right? We took our 80 grams and converted it into moles. So we actually already have this math work written out. We actually already have the answer. So I'm just going to basically rewrite this. There's no need to reinvent the wheel, right? So it was 80 grams of copper to begin with. Molar mass was 63.5 grams of copper to 1 mole. Okay, when my grams of copper cancel. And we got 1.26 moles of copper as our number. Okay, so now from here, we're going to convert moles of copper, to moles of copper 1 sulfide. That's the product we're trying to get. And this is a 2-to-1 ratio. So we can set up our fraction. So for every 2 moles of copper, okay, every 2 moles of copper, that comes from here, okay, 2 moles of copper, that's what's written here on the bottom, we make 1 mole of copper 1 sulfide. Okay, and again, this 1 to 2 ratio, this fraction I just wrote, comes from this. 2 moles of copper to 1 mole of copper to 1 sulfide. Okay, 2 to 1. And I'm writing it like this because I'm starting with moles of copper, so I want moles of copper on the bottom so that it cancels. Okay, we're using dimensional analysis here. So if we do this out on our calculator, we will take 1.26 divide by 2 equals, and we get 0.63 moles. We're going to go 0 just to keep it 3 significant figures. Moles of copper 1 sulfide. I keep saying copper 2. It's copper 1 sulfide. Okay, so here's our moles of copper 1 sulfide. Lastly, we're going to convert that to grams, and the reason we're going to convert that to grams is because in the problem, okay, on the slides, which is not being shown right now, it is asking for what is the maximum number of grams of copper 1 sulfide that can be formed. Okay, so they don't want moles, they want grams. So we got to just take our 0.630 moles of copper 1 sulfide and convert that into grams of copper 1 sulfide, which to do that, we will need to use the molar mass of copper 1 sulfide. Okay, to go from moles to grams, we need molar mass. So if we look on the periodic table, we'll have to add up some numbers here to find our molar mass. So copper has a molar mass of 63.5 grams. There are 2 of them. Okay, so we got to times that by 2. So real quickly, 63.5 times that by 2. This is 127 grams from the copper. Then we have the sulfur, which there's only 1 of, and sulfur has a molar mass of 32 grams per mole. Okay, so if we add these together, 127 plus 32, we get 159 grams per 1 mole for the copper 1 sulfide molar mass. Okay, so here's our molar mass. Hopefully that's still visible. Okay, so there's our molar mass. So since we're starting with moles of copper 1 sulfide, we're going to have the 1 mole of copper 1 sulfide on the bottom, 159 grams of copper 1 sulfide on the top. That way moles of copper 1 sulfide cancel and we'll get into grams. Okay, so we're basically just going to take 0.630 times 159 equals, we get 100.17, and I guess if we want to round to 3 significant figures, let's just write it as 100 and then a decimal point at the end, which looks kind of funky, but 3 significant figures. There you go. So about 100 grams. That would be the maximum amount of copper 1 sulfide we can make. All right, so let's switch back to our slides here. All right, we're back. So I'm just going to insert a text box here real quick. Again, the math work is all shown on our paper. It's just easier to do it that way. So we have about approximately 100 grams of copper 1 sulfide can be made. There we go. Okay. So let's talk about then percent yield. Okay, so that's the second half of these notes. So the first half, of course, is just limiting reactant. What is limiting reactant? How do we calculate limiting reactant? And how does it work? The next part is percent yield. So percent yield is a measure of the efficiency of your chemical reaction when you carry it out in a laboratory. A batting average is a percent yield, which is basically like out of, how many hits that you're hitting, or how many times you're up at bat, how many times you're actually hitting the ball. Obviously, you want to get a percent yield that's 100%, right? Like you want maximum percent yield. And in a chem lab, when you do a chemical reaction, you might think that you're going to make this much material, right? You might calculate it and go, here's how much I should make based on my calculations. But then you do it in real life and you don't actually make that much. And there's a lot of different factors for why you don't make that much. Some of it can be because of human error. Let's say that you calculate out that you should make this much, but when you're doing your lab, you spill some stuff on the table. Maybe when you're pouring, some of it dribbles down the side of your beaker. Maybe when you're measuring things on your scale, some of it falls onto the scale and you don't scoop that up. So there's a lot of different things that can like mess up your numbers. Or you do a chemical reaction, and in that reaction, you actually have side reactions that take place. Side reactions are basically when another chemical reaction happens that you didn't plan for, or that maybe you didn't realize was going to happen. So instead of making all the product that you thought was going to be made, you also make this other stuff that you didn't plan for. But that will, of course, then make the product you wanted be less because some of it is making something else. Right? So there's a lot of different factors for why your percent yield will not be 100%, but you're trying to get 100%, but you'll never, ever typically get there. So the theoretical yield is the maximum amount of product that you can form based on calculations and calculating how much stuff you're starting with. Okay, that's a theoretical yield. So like in theory, this is how much you should make based on calculating it. But the actual yield is what you actually make when you do the lab in real life. Okay, and basically the percent yield then is going to be your theoretical yield compared to your actual yield and how far off you are. It's kind of like a percent error, basically. So percent yield is going to be the ratio of your actual yield to your theoretical yield, and then times 100 to get it as a percentage. So like imagine, theoretically you should make 100 grams of some product, but when you do it in the lab, you actually only make 80 grams. That means you have a percent yield of about 80%, right? You made 80% of what you should have. Now again, as to why is there 20% of your product missing? Could be a lot of different reasons. But either way, that's what percent yield is. So let's go over an example of a percent yield problem here so we can understand what they want us to do and how we solve them, okay? And I apologize, I'm a little bit sick here, so if I sound a little bit congested, that is why. So it says calculating the theoretical yield of a reaction. So calcium carbonate, which is found in seashells, is decomposed by heating. The balanced equation for this reaction is CaCO3 solid plus CaCO3 solid breaks down. The little triangle means that there is heat being applied, and then you get calcium oxide and carbon dioxide gas. So the question is, what is the theoretical yield of calcium oxide if 24.8 grams of calcium carbonate is heated? Okay, so again, in order for us to understand what this problem is asking from us, we're going to do this on paper, but I will again explain what they're actually asking and what we are trying to do here, okay? So we have this compound that is going to break apart, okay? It's decomposing. They want us to figure out how much calcium oxide should we be able to make if we are starting with 24.8 grams of calcium carbonate, okay? That's what they're asking. So pretty much this problem is just taking 24.8 grams of calcium carbonate, okay, this material, and converting it into grams of calcium oxide, this material. Okay, that's it. That's all we're doing. Pretty much just like the problems in chapter 12, section 2. We're just going from grams of calcium carbonate to grams of calcium oxide. That's it. Okay, now there will probably be follow-up stuff after this problem, but that's all we're doing for now. So let's switch our camera over. Let's rewrite our reaction here just so we can have it. And then we will do our calculation. Okay, so our reaction looks like this. And I am going to check real quick just to make sure that it is balanced. It does say that it is balanced. Yeah, we're good. Okay, so here's our problem. If we're starting with 24.8 grams of calcium carbonate, how many grams of calcium oxide can we make? Okay, that's what a theoretical yield is. That is, how much stuff can you make based on what you're starting with? Okay, and it's all just calculation. So this is just like every other problem we've done, right? Step 1, you should know what step 1 is. If you know what it is, say it out loud. Okay, so it's going to be convert grams of calcium carbonate to moles of calcium carbonate. Okay, step 1 is always going to be convert to moles, like every problem ever in these chapters. Step 2, we are now then going to convert moles of calcium carbonate to moles of calcium oxide, okay, because that's what we're trying to get in the end. And then lastly, step 3, they want us to get this into grams, so we are going to convert moles of calcium oxide to grams of calcium oxide. Okay, so pretty much exact same steps as all the other problems we've done so far for this chapter other than the limiting reactants. Okay, so let's start with 24.8 grams of calcium carbonate. If we're going to get this into moles of calcium carbonate, we are going to need to know the molar mass of calcium carbonate. Okay, so we're going to have to do some calculation here real quick. So calcium has a molar mass of about 40 grams. So 40 grams for the calcium. Carbon has a molar mass of about 12 grams. So 12 grams for the carbon. And then oxygen is 16 grams. And of course times that by 3 because there's 3 of them here. So let me do this on my cell phone here real quick. 16 times 3. We get 48 grams for the oxygen. And if you add all these together, so 48 plus 12 plus 40, we get a molar mass of about 100 grams per mole. Okay, so here's our molar mass. So 100 grams per mole. We're starting in grams of calcium carbonate, which means that we want to have the 100 grams of calcium carbonate on the bottom of our fraction, the 1 mole of calcium carbonate on the top of our fraction. That way our grams of calcium carbonate cancel and we get into moles. Okay. So we're going to take 24.8, 24.8, there we go, divide by 100 equals, all right, so we get 0.248 moles of calcium carbonate. Okay, so there's our moles of calcium carbonate. Step 2, we're going to convert those moles of calcium carbonate into moles of calcium oxide, CaCO3. Okay, now all of these are 1-to-1 ratios. Okay, 1, 1, 1. We'll notice there's no number written in front of any of these chemical formulas, which means that it's just a 1, a 1, and a 1. So for this second step, any amount of calcium carbonate we have as moles will be the exact same amount of calcium oxide as moles. So we actually even don't need to really do this step because they're going to be equal. Okay, so 0.248 moles of calcium oxide. Okay, now again, the reason I can do this is because it is a 1-to-1 ratio. So the exact same amount of moles of calcium carbonate will make the exact same amount of moles of calcium oxide. It's a 1-to-1 ratio. I don't need to do any math work. Okay, these are exactly equal to each other. So step 3 then, we are going to take that moles of calcium oxide and convert that into grams of calcium oxide. And to do that, we are going to need to know the molar mass for calcium oxide. So we have the molar mass of calcium right up here, which is 40 grams. We have the molar mass of oxygen right up here, which is 16 grams. We add those together, 40 plus 16, I can do this in my head, that is 56 grams of calcium oxide per 1 mole of calcium oxide. Okay, so there's our molar mass. Since we're starting in moles of calcium oxide, the 1 mole of calcium oxide will be on the bottom of our fraction like this. The 56 grams of calcium oxide will be on the top of our fraction like this. That way, moles of calcium oxide cancel with each other, and we're basically just going to take 0.248 times 56. So 0.248 times 56 equals, and if we want to round this to 3 significant figures, we'll take this as 13.9 grams of calcium oxide. Okay, so again, the question, and I know it's not being shown right now on the screen, but the question was, what is the theoretical yield of calcium oxide if 24.8 grams of calcium carbonate is heated? So the question basically is saying, what is the amount of calcium oxide that we can make if we're starting with 24.8 grams of calcium oxide? Based on our calculations, 13.9 grams of calcium oxide should be able to be made. Okay, so let's switch back to our slides here. Let's just insert a text box. Again, I know the math work is not being shown. It was done on paper. I'm just going to type in an answer here. But we can say that 13.9 grams of calcium oxide should be able to be made. Okay, that's our theoretical yield. Now, I'm guessing the follow-up question is going to do something with percent yield. Okay, so let's go on to the next question, and here's what it says. What is the percent yield if 13.1 grams of calcium oxide is actually produced when 24.8 grams of calcium carbonate is heated? All right, so here's the follow-up, and I figured this was coming. So we first calculated theoretically how much calcium oxide we could make. Okay, based on our calculations, we could make 13.9 grams. This problem now is saying, what is your percent yield if 13.1 grams of calcium oxide is actually made when you have 24.8 grams instead of 13.9? Okay, that's the question. And basically, again, I'm going to just switch my camera back here so that way we can look at paper. Okay, so on our paper here, again, we started with 24.8 grams of calcium carbonate, and that can make 13.9 grams of calcium oxide. Okay, that was our calculation in the previous problem. So this is our theoretical yield, okay, because this is just based on our calculations. And now the problem on our slides is saying, actually, you only make 13.1 grams of calcium oxide. So what's your percent yield? Okay, that's the question. What's your percent yield? So to do that, percent yield is equal to actual yield. So actual yield divide by theoretical yield times 100 to get a percentage. Okay, this is our equation, which is in the notes in the slides. Okay, so all we're going to do is we are going to take 13.1 grams of calcium oxide, divide by 13.9 grams of calcium oxide, and times 100 to get a percentage. And again, in like the best scenario, we would want this to be 100%. But realistically, it will never be 100%. Okay, but you want to get as close as you can. So I'll show the calculation here. Okay, so 13.1 divided by 13.9, and then times 100. And just to round to three significant figures, we get 94.2%. Okay, that is our percent yield. So we did not make 100% of what we should have, but 94.2% is pretty good, right? That's not a bad percent yield. Okay, so let's switch back to our slides. And we're just going to insert a text box here. And again, we showed the math on our paper, but we would say our percent yield is 94.2%. All right. So that is it for this section of notes and those problems. Of course, there are practice problems at the end here. There will be a video of me going through the quizzes and going through those problems to show you how they are done. But otherwise, hopefully that helped you. Again, I tried to do my best to explain every one of those problems and go slowly. So thank you so much for sticking with me. As always, if you have any questions, make sure you reach out to me so that I can help. All right, guys, I'll see you in the next one. Bye.